Hello everyone, today in this video we'll be discussing the third module of data communication, and this module has three topics. The first one is bandwidth utilization, the second one is switching, and the third one is error detection and correction. So let's get started here. So in the first topic we have two subtopics, which is multiplexing and spread spectrum. Okay, so I'll be going very slow to give you a whole picture of what the thing is, and I'll be just covering the important topics here. Means there's much lot in the notes, so I've just picked up the important topics from the exam point of view. Okay, so make sure you watch the video till the end, and if you like this video, hit the like button and don't forget to subscribe to my channel. Okay, so let's get started with the first topic, multiplexing. See here, consider the multiplexing as a highway. Okay, so suppose that this is a gate. Okay, consider this as a gate, and four cars are coming: car A, car B, car C, and car D. This is one road. Okay, these are four different roads, and from four different roads, four cars came. And in this road, you can have in parallel four cars can go. Okay, like car A, car B, car C, and car D. Okay, if four cars can go parallelly, that can be combined in the single highway. Okay, this is what is actually multiplexing means. In four signals are coming like this. Okay, and this will be multiplexed into a single link. Okay, this is known as a link, and these are known as channels. Okay, individual channels. So by the name only we can understand bandwidth utilization. Bandwidth means how much the wide it is, means the highway is how much wide, that is bandwidth. Okay, and utilization means utilizing the complete bandwidth. So instead of sending only one car here like the normal analog signals, see, this is the bandwidth here. If you are just sending one car from here to here, if you're sending just one car from here to here in the one bandwidth, it will be not utilized till the maximum extent, because many cars can be sent at the same time. So to utilize the maximum bandwidth is called as bandwidth utilization. So in multiplexing we do the same thing: n inputs and one channel. And demultiplexing means the opposite of multiplexing, wherein one channel will have the separate paths from that same channel. Okay, this is known as demultiplexing. So the three ways of multiplexing. First one is frequency division. Okay, frequency division means, see here, this is the input. Okay, three inputs are there with different frequencies. These are the signals here. Okay, we'll be seeing an example here below, but let's first understand what it is actually. So it will be multiplexed into three channels here, and between that there will be guard channels, which will avoid the overlapping of the near channels. Okay, so let's see by an example here. Consider an example of F1, F2, and F3. These are three signals of frequencies F1, F2, and F3, which are combining at the single location here. Okay, this will multiplex it into one signal. Okay, and this signal will be transferred. So the condition is that if suppose the frequency is 10 and this is 20 and this is 30, and the maximum allowance of this is 70. Okay, at that time this will be added. 10 plus 20 plus 30 is 60. Is 60 less than 70? Means does this bandwidth support the sum of these frequencies? If yes, then it will be transferred. Okay, else it will not be transferred. So this is one condition, and after that the channels are separated by guard bands. Okay, see, as you can see in this diagram, the channels are separated by guard bands. Okay, to avoid overlapping. Okay, and then when it comes to the receiver end, at that time it will be demultiplexing. Okay, that means the main frequency which was sent here, that will be separated into f1, f2, f3. Okay, let's see how the questions can be asked in exam. Assume that a voice channel occupies a bandwidth of 4 kilohertz. So this is the frequency of 4 kilohertz, each of these 0 to 4. We need to combine three voice channels, these are three voice channels, into a link with the bandwidth of 12 kilohertz. So the total capacity of this is 12 kilohertz. Okay, from 20 to 32. From 20 to 32 it is 12 kilohertz, right? So that will be divided as follows: the first bandwidth will be from 20 to 24, the second one 24 to 28, and third one 28 to 32. So 20 to 32 all will be utilized, and that will be sent to the bandwidth here. Okay, three signals, these three are here. Okay, this will be sent and it will be demultiplexed at the receiver end. Okay, from 20 to 32 it will be separated, separated as 20 to 24, 24 to 28, and 28 to 32. Okay, so these are the three signals which were sent initially. Let's understand what is analog carrier system. Observe carefully here. These are the three signals, okay, with the frequency 4 kilohertz. This F1, F2, F3. But in this case, all F are equal to 4 kilohertz. Okay. So these 3 4 kilohertz, it's actually not 3 here. If you see here, observe carefully, 1 2 and dot dot and n means n number of channels are getting input here. Okay, how many? It's 12 channels. Okay, n is 12 here. So 12 channels of 4 kilohertz frequency each are transmitting from here. Now can you tell me how much is the total frequency output from here? It is 12 into 4 because each is 4, so if you add up it will be 12 into 4. So the total frequency coming out from here is 12 into 4, 48. Okay, 48 is coming from here. So in the same way another one is coming from here, 48. Like that, this number is also 12. Okay, so 12 channels of 48 frequencies are in the second stage. This is the first stage, 12 channels of 4 frequency, and second stage 12 channels of 48, and then in the same way it is becoming greater and greater. Okay, so in this way we can transfer a lot of signals in a single link. Okay, so this is known as analog carrier system. So this is all what we need to know under the topic. First one, frequency division. Okay, let's move on to the second one, which is wavelength division multiplexing. In wavelength division multiplexing, it's the same as the frequency one, but here we will be dividing the wavelength. Okay, in this the different wavelength signals will come, and that will be combined in a single wavelength, and that will be demultiplexed in the receiver end. Okay, so in the notes it was given this much only, and it's not that important as compared to the previous one. The most important one is time division multiplexing. Okay, let's see what it is. In time division, the instead of bandwidth the time is shared. Means if four signals are coming here, 1 2 3 4, each will be given us a slot of time. For one it will be this much time, then 2, then 3, then 4, then again 1 2 3 4, like that. Okay, group will be sent together. Okay, giving each one equal amount of slot time. Okay, and that will be demultiplexed at the receiver end. Okay, instead of bandwidth the time is shared. That's the only difference. And there are two types, synchronous TDM and statistical TDM. So let's discuss what is synchronous TDM. There are some terminologies like time slots and frames. So see here, observe it carefully. A, B, and C. These are the three signals getting sent. Okay, and these three signals are divided into three parts: A1, A2, A3, and B1, B2, B3, C1, C2, and C3. Okay, each of equal slots. Okay, equal slots of time, like 1 second. Okay, for each, 1 second of A and 1 second of B and 1 second of C will be sent together as a single frame. So as you can see here, a single frame consists of A1, B1, and C1, each having 1 second. So total time will be 1 plus 1 plus 1, total 3 seconds. Okay, so like that many frames will be sent one by one. And see here, each frame has three time slots. Okay, A, B, and C, and each time slot is duration is T by 3. Okay, if total time is T, the each slot will be T by 3. Okay, the next concept is interleaving. Interleaving means you'll have two rotating circular coils here, and what these coils will be doing is they will be synchronized here. Since it's rotating anti-clockwise, what we can consider is, if this is picking up A1, okay, then it will rotate and come. This will pick up B1, and then this will pick up C1. So each slot, A1, B1, and C1 will be attached. Okay, and then it will be sent to this frame. Okay, each frame will have A1, B1, C1. Okay, and that will be sent to the receiver end, which will be receiving one by one. So this will receive A, this will receive B, and this will rotate and come and receive C. Okay, so the timing is synchronized so that proper transfer will take place. This is known as interleaving. Okay, the next one is empty slots. See here, three signals are getting transferred, but in some of the signals there are some empty gaps here. So due to that, what happens is, in each frame there will be some empty slots here, which will waste frames. Means memory utilization will be inefficient. So to make it more efficient, what we can do is we can follow some management techniques like multi-level multiplexing. For example, see here, what are the inputs here? Just consider the inputs for now: 20, 20, and rest all are 40. So if you want to send that in the multiplexer, how can we send? Each frame will be of 40. Okay, many frames will be there, each will be of 40. So since we have one input as 20, we'll send as 20 here, leaving this empty. Second is also 20, it will be sent here, this will be empty. And third one will be utilized in full because it is 40. But here empty slots are there. This is wastage of memory. What we can do is we can put a multiplexer in between 20 and 20 to make it 40, so that 40 will be sent along with the other channels. Okay, so that the memory will be utilized. This technique is known as multi-level multiplexing, because we are not just multiplexing in a single level. In the multi-level, we are multiplexing. Okay, so this is the first one, and the second one is multiple slot allocation. Okay, suppose that 50 is one of the inputs and the slot is just of 25. So 50 cannot be allocated here. For example, each is 25. Now 50 is the input. How can we allocate 50 in it? What we can do is we can use demultiplexer. It will divide the 50 into two parts, 25 and 25, so that each will be fitting in the slot of this multiplexer. Okay, so this is known as multiple slot allocation. For a single slot, multiple slots are allocated. Okay, and the third one is pulse stuffing. Pulse stuffing means if one of the inputs is not of the complete frame, like for example, it is 50, 50, and it is 46. This can be upgraded to 50 by using pulse stuffing. Okay, then each frame will be utilized in full. Okay, without leaving any gaps. Okay, this technique is known as pulse stuffing. And the next one is frame synchronization. See here, to avoid the errors in the transmission, a pattern is sent to the receiver. Suppose that this is a transmitter and this is the receiver. Both will have a same code here, 101 and 101. This will send the data in the form of packets, and each packet will have one number, 101. This will be sent to the receiver, and the receiver will check if the arrived data is having the same code or not. If it has the same code, that means no error has taken place in the transmission. Else there has some error, because if the code changes, that means some data is lost, or some data is added here. Okay, so in that way the frames can be synchronized to ensure the error has happened or not. Okay, and we discussed the first one, which was this one, synchronous TDM. The second one is statistical TDM. Okay, in statistical TDM, no slot is left empty. Only when the sufficient data is there, then a frame is created. Okay, so suppose that there are two situations. One is the synchronous and second is the statistical. In synchronous, what happens is, see here, in this case the input is 1 and input is 2. In synchronous, the for 2 one frame will be allocated, and for 1 another frame will be allocated, leaving behind one empty space here and two empty space here. Whereas in statistical, what happens is, if there is 3 frames in total, then only the frame will be created. If there is less than 3, it will wait for the data to arrive. Okay, so that's the main difference between synchronous and statistical. Here are a few more examples which depict the same concept. Okay, so the first topic is over, which was multiplexing, and the second topic of bandwidth utilization is spread spectrum. Okay, spread spectrum means, the see here, if this is the bandwidth. Okay, means a bandwidth you can consider as a box. Okay, and the data which you send is like a gift. Okay, what gift you can send? If you put it in a equal size of box, that means it's very unsafe. Means the distance between the gift here and the external world will be very less, so that errors can happen very easily. Whereas if you put it in a big box here, like if it's a very precious gift, you can put it in a big box, so that probability of errors happening at this point in a bigger area is lesser. Okay, so that's known as spread spectrum. So in this case, what we do is the data to be transferred will be sent in a wider spectrum. Okay, so that suppose that this is the data here, and if any errors happen, it can happen here and here. It's very less that it will come to here. Okay, whereas if we send in the smaller spectrum, it will fit in it, but errors can happen very easily. Okay, there are more chances of errors because the spectrum is very small. Okay, so that's known as spread spectrum. There are two types mainly. First one is frequency hopping spread spectrum. Okay, so suppose that this is a signal which is getting transmitted. Okay, if the frequency is changing very often, okay, unauthorized access cannot corrupt the data because they don't know exactly in what frequency the data is getting transmitted. So it's very hard for them to corrupt the data. Okay, that's known as frequency hopping spread spectrum. And the next one is direct sequence spread spectrum. Okay, this is the original data which is to be sent. Okay, for each bit there will be some code here. Okay, there will be some code here, and what is transmitted is this code, not this data. This code will be transmitted, so that for suppose that for 1 it is 1111010. For 0 it is 111100. Okay. So if the attacker changes some code here, we know that only two possibilities are there, either this one or this one. Okay. If the attacker changes some code like the attacker makes the first two codes as 0, we'll obviously know that this is not existing code. So we'll know that it's an error happened here, and whereas it should be 1 1 here. So in that case, we can easily identify this code and the code for which it represents, which is 1. So we'll know that the signal which we received is 1. Okay. So in this case, we can save the data from getting corrupted. Okay. Is switching. Switching means there are multiple devices here. Each will be connected by using switches. Okay. So these are all switches for having one-to-one connection between the devices. Okay. So A and B are connected in this switch by using this switch, and A and E are connected. A and F are connected by using this one, and so on. Okay. So there are two methods mainly used, which are circuit switching and packet switching. Let's discuss the first one. See, for each switching there will be multiple layers, which is the physical layer, data link layer, network, and application layer. Okay, so this is discussed in much detail in the module 2. It are just these are just the layers which in which the data transfer will be taking place. Okay, so what is circuit switch network? In this there will be mainly four switches here, and these four switches will be having all the connections from the different directions. And suppose that A device has to send some data to M device. Okay, what will happen is it will send the device to switch 1, and that will send to switch 4, and this will send to switch 3, and this will send to M. Okay, so the three phases: the first one is connection setup, second is data transfer, and third is connection teardown. That means firstly the connection will be set up between the A and the M, means this is the path, and when it's set up, then the data will be transferred, and after the data is transferred, it will break down. Okay, these are three main phases in each transmission. Okay, then the second one is packet switch network. In this, the message is divided into packets of fixed length or variable size. That means if a message is of size 10, it will divide into two or like five parts, which will, each one will be 2 2 2 2 2. Okay, so in that way the data is sent in the form of packets. There are two types. First one is datagram networks. In datagram networks, these will be the switches here, which will be having the connections with each other, and this is the source and this is the destination. When a packet is sent, it has the source address and the destination address. Okay, suppose that this is the packet, source, destination, and the destination address, and here the message will be sent. Okay, so this will be sent to the packet switch 1, and switch 1 will send to the switch 2, and then to 3, and then finally to the destination. Okay, so each packet has a header. So header has the source and the destination address. Okay, and the switch recognizes the destination. See here, the using the header, the switch recognizes the destination. Okay, so there will be a table maintained which will have the destination address of the output data. Okay, the second one is the virtual circuit network. Okay, In this, it's a combination of the circuit switch network and the datagram network. Okay, so in this case, these are the switches, and these are the end system. Okay, so there are two types. First one is global addressing, and second one is local addressing. In global addressing, it has the address to reach the destination. Consider, for example, I'm starting from this point A and going to point B. Okay, I've sent a packet here. In global addressing, it will have the address of B, direct address of B. It will go to here and it will find the shortest path to B. In the second case, in the local addressing, it will have the address of switch 1, and switch 1 will change the address to switch 2. This will change the address to switch 3. So data will be transferred one by one after changing the addresses. Okay, and finally it will go to the destination. That's known as local addressing, and it has three phases, the same as the previous one. Setup phase means the source will set up the phase with the destination, and it will send a confirmation message that the path is set. After that, the data will be transferred, and after that, the teardown phase means sources sends a special frame called teardown request, and destination B responds with a teardown confirmation frame. After this point, the path will be broken down, and the data transfer will be completed. Okay, this is the last topic, which is error detection and correction. Okay, so there are mainly two types of errors: single bit error and burst error. Single bit error means, consider an example here. This all data is same, but here an error has happened. Error happening in a single bit is known as single bit error, and burst error means multiple errors happening at the consecutive memory locations. Okay, so more common is the burst error. So there are few techniques by which we can check for errors. First one is block coding. In block coding, k bits of data is sent to the generator, which will generate some extra bits, and then total will be n bits. So see here, this is the original data. Extra bits are r, so total number of bits will be n, and then this code word will be transferred to the receiver, and the receiver will receive n bits. It will discard the extra r bits and take the k bit data. So let's see how it actually works by considering an example of parity checker. Okay, but before that, what is Hamming distance is defined as the maximum number of chain bits detectable. Okay, so if the Hamming distance is 2, that means the changes happening in the 2 bits can be detected. Okay, so let's discuss about the parity checker. In this, it ensures that see, this is the real data. Okay, k is the real data, 0 0 0 1 1 1 and 1 0, and we have added these bits. How will we add if you have to add 0 or 1? See here, total number of ones should be even. Okay, 1 should be even. In this case, total number of ones are even because it's 0. In this case, it's 0 1, so we have to add another one to make the total number of ones as even. So we have added here 1. In the third case, 1 and 1, two ones are there, the total number of ones are even, so we'll add here 0. Okay, in the third case, we have added here 1 to make the total number of ones as 1. Okay, total number of ones as even. Okay, so in this way, the parity bit will be generated by a generator. See here, this is the data word which is sent, means this is the data word. For example, 0 1. Okay, that is sent. 0 1 is sent, and this will go to the generator, and 0 1 will be here, and the generator will generate either 1 or 0 based on how many 1 are there. In that case, in this case, a single 1 is there. To make it even, another 1 should be added, so the code word generated here will be 1. So total number of 1s will be 0 1 1, and this code is sent to the receiver. Okay, and when 0 1 1 comes here, it will be checked if the total number of ones are even. If it's true, the data will be accepted and the extra bit will be removed. Okay, so the real data, which is 0 1, will be received at the receiver end. Okay, this is known as block coding. Okay, the second technique is cyclic codes. In this, the first one is cyclic redundancy check. Okay, so let's consider an example here. This is the same thing. Data word is sent, and the generator generates a code, and that will be added to this code word, and code word will be transferred, and then it will be checked here, and the extra bits will be removed, and the data word will be received. Okay, but the thing which generator does is different. Let's see by an example. Let's see by an example what it is. suppose that the data to be transmitted is 1001. Okay, this is the data 1001. Okay, let's see what the generator does. See here, the data is 1001, and what we'll do is first we'll add 3 zeros. Okay, so it will become 101, 1001, 000. Okay, so we'll write here 1001 and 000. We'll be dividing it with any of the divisor, like in this example 1011. Okay, and this is the data to which 000 is added. Okay, and then when we divide it, like for example, how to divide? See here, 1011 we will be seeing here 1 ones are 1, 0 ones are 0, 1 ones are 1, 1 ones are 1. Then we'll be subtracting. It will be then it will be 1 minus 1 0, 0 minus 1 1, 0 minus 0 0, 1 minus 1 0. We'll be bringing down 0 here. Then again we'll be seeing 0 1 0 0. Only the first bit you have to see here, and first bit is here. 1 zeros are 0 right here, 0, and then 0 zeros are 0, 1 zeros are 0, 1 zeros are 0. Subtract it, we'll get 1000 after bringing down the second 0, and then see the first bit here 1. So 1 ones are 1. Like that we'll be doing till the end, and at the end we'll get some remainder here which is 110. Okay, after getting the remainder we'll be adding this remainder to the dividend. Okay, so what will be the code? 1001, this same code. Then after adding the remainder we'll get 110. This is the code which will be sent. See, there is a logic here. If we divide some number, like for example, if we divide 5 by 2, it will be 2 to the 4 minus 1. Now, if 1 is added to 5, then it will become 6. Okay, and then it will be completely divisible. 2 3s are 6, and here no remainder will be there. So when we add the remainder to the dividend, it will become divisible. So that's the same thing. If the remainder is added to the dividend, it will become completely divisible. Okay, that's what's happening here. This code word which is 1001 and 110, this is the remainder. It's completely divisible by this divisor 1011. Okay, that will be checked at the receiver end. We'll be dividing 1011 with the code 1001 110. When we divide it, it will become 0. Okay, in the remainder. If the remainder comes 0, at that time the transmission happened without errors. If it does not become 0, means there happened to be some change in the transmission. At that time the error will be detected, because see here, what was the data getting transmitted? This one 1001 110. If it changed to 1000, here it was 1, right? This is the correct data. See here, a change happened here, rest all is same. But if we try to divide that by 1011, it will not give us 0. Okay, so in that case it can be known that there is a error here. So the checker will be see, this is the checker. It will reject the data because it's not coming 0 at the remainder. So that will be that message will be discarded. Okay, else in the case if the data is correct, at that time the extra bits which are 110, this will be discarded, and the data which is 1001 will be received. Okay, so data transmitted here 1001 will be received here also 1001. Okay, the next method is polynomials. In polynomials we will be having the terms here, means if the data is 1 0 0 0 0 1 1, what we can do is assign the values 0 bit, 1 bit, 2 bit, and till 6 bit. Okay, then wherever the terms you can find as 1, at that place we will be taking as 1 into x power the bit number, 0 into x power the bit number, wherever 0 is there. So for example, if you see the data here, it will be 0 bit, 1 bit, 2, 3, 4, 5, 6. Where all 1 you can find. 1 is here, here, and here. So I'll be writing the polynomial as x power 6 for this one, plus x power 1 plus x power 0, which is 1. Okay, so this is the polynomial for this data. Okay, and we'll be doing the same thing for the polynomial also. The data word is 1011, so it will be 0 bit, 1 bit, 2 bit, and 3 bit. So 3 bit is 1 x cube, and 1 bit is 1. 0 bit is 1, so it will be x power 0, which is 1. So this is the data word to be transmitted, and we can choose any divisor. So in this case I have chosen 1011 x cube plus x plus 1. We'll divide the polynomial as normal division, and we'll get the remainder here. Then we'll add this remainder to the dividend. Okay, so this will be the code word, and then this code word will be sent to the receiver. It will receive the code word, and then it will divide by the same divisor. At that time it will become 0 here, in case there is no error happened in the transmission. If there is any error, or if the code word changes, at that time remainder will not be 0, and it can be known that there happened some error in the transmission and the data is not correct. Okay, so the same concept as the previous one getting implemented in the form of polynomials. Okay, this is the last topic, and it's very easy. If you have to send the numbers 7, 11, 12, 0, and 6, what we'll be doing is we'll send these numbers along with that the negative value of the sum of these. Okay, what is the sum of 7, 11, 12, and 6? It is 36. So along with all of these numbers we'll be sending minus 36. So what happens is, in the receiver end, the numbers received all should be added. So when we add all of this till here, it is 36, and minus 36 will be added, so it will become 0. If it becomes 0, then it is accepted, because all of these numbers sum should be 36. If any of the number has been edited, at that time the total sum will not become 0. That in that way we can recognize that the some error has happened here. If it becomes 0, at that time no error has happened and the message is correct. Okay, so in that way you can identify the errors using checksum. Okay.